Thank you for having me. So in particular, Timescale is a general purpose time series database, but increasingly we see ourselves, one of the applications of time series, of course, is actually metrics, server metrics. So time series, of course, are much broader than that. They're in finance and IoT and industrial and logistics. But certainly a lot of people probably in this company, or sorry, in this room, think about how do we use those for metrics. And increasingly, platform for doing this, Prometheus, particularly given the adoption of Kubernetes, these are often used together. And so I actually want to talk about Postgres, this old school database with Timescale being used as persistent storage for Prometheus metrics. And so you could say, this is strange. Aren't there all these like new cool databases like invented in San Francisco that would be good for metrics? And I want to make the case, so the same reason why we ultimately built Timescale on top of Postgres is there are a lot of good reasons for it. In particularly, if you have an important database, we say you like your database to be boring. We like your database not to wake you up at 3 a.m. because there was this corner case that the new thing in Rust didn't really figure out. And that from something like Postgres, you get really 20 years of reliability, ease of use, a broad ecosystem. So all of your tools basically probably speak to Postgres. In fact, things like flexible data types. It's not just about, even with structured schema, if you want JSON support, Postgres and MySQL probably have better support than this than a lot of the NoSQL databases that introduce them. Even things like geospatial support. And particularly, and this is often used for time series, is the power of joins. So when many people think of time series, they think of just one stream of data with some labels. But if you're thinking about, like, let's diagnose why some service might be bad or why some industrial machine went bad, you often want to ask questions about the device, about its maintenance records, about other things. That would be very useful to be able to join to it, rather than trying to denormalize this data on every data record. Now, you could say, except, there's a lot of problems with Postgres too, right? In that it's hard or impossible to scale. If you have this constant stream of data, you want to delete data because ultimately you can't store all of it for fine-grained events or metrics. Vacuum deletes are expensive. SQL is too complex or has poor support for querying time series, and I really don't want to, every time I change something, redefine my schema. And so I kind of want to talk about some of these things and how basically Timescale and also Timescale combined with Prometheus addresses many of these perceived shortcomings. So the first one, hard or impossible to scale, probably the best one. This is a kind of a graph that we like to show. This is the ingest rate doing single row inserts. If you want to, most databases to increase throughput, you want to do a little batching, but I think it's fairly demonstrative by looking at this. Single row inserts, you're starting to do 15,000 insert transactions per second. Postgres is happy. Your database starts at 5 million, gets at 20 million, and then it goes off a cliff. And what, of course, is happening is your database is quite happy when everything is in memory. You don't ever basically have to touch disk. But the minute you basically exceed the capacity of your main memory and you need to start swapping your indexes to disk, this is when your throughput really suffers. So we've gone from 15,000 inserts per second to a few hundred inserts per second. In batch mode, you can go from 100,000 rows per second to, again, 1,000 rows per second. That's not really where you want to be. And so this, in some sense, is where Timescale comes along, and I'm going to talk a little bit about it, but how we basically solve the scalability problem. And so once we solve the scalability problem, we could scale ourselves to time series workloads. We could overcome some of the other problems with deleting data and giving more advanced analytics for time series analytics. And the last thing, I said there's really kind of two problems people saw with using relational data. One was scalability, and the other was I really don't want to define my schema. Maybe if it's something really kind of business use case, you'll spend some time defining your schema. But you're saying, I just want to throw a whole bunch of server metrics at it, and I don't want my DBA to have to redefine their schema every time I plug in a new APM tool, right? And so, but once you combine it with something Prometheus, and I'll talk to you a little bit about how we did that, we could do something like automatic schema creation in the database and be able to basically give this backend for Prometheus visualized. I saw Baron actually showed Grafana, I think, in one of your images, allow you to visualize Grafana to Prometheus and Grafana to Timescale without ever dealing with anything like schema creation. And so that's what I want to talk about today. So some of you might be familiar with, just a quick show of hands, how many people here are familiar with Prometheus? Okay, a couple. So Prometheus is one of these metrics tools that goes out and polls a lot of servers. So it'll poll things like disk stats and IO stats and load readings. You know, the proc file system is great for polling. Prometheus will go out, bring these back in, and itself has some storage. But that storage is a little bit, and many tools like Grafana will actually interface natively with Prometheus. They have a query language called PromQL, and you'll be able to visualize those metrics inside Grafana. But recently, Prometheus also added support for remote storage API. And this is so because in some sense, Prometheus was not really designed for long-term storage, and its PromQL query language designed to be very simple, but perhaps isn't excessively powerful. Right? And so this is where Timescale came in, and we actually built against their remote storage API. And so now, basically, we get all the data pushed to us. We kind of pull the data from Prometheus and insert it into our database through an adapter, a special Postgres, Prometheus to Postgres adapter we wrote. And we also published and open sourced a Postgres extension called PG Prometheus. So I should have clarified this before, that Timescale is actually implemented as an extension inside Postgres. So you're running a Postgres database with Timescale installed on it. We have this other one called PG Prometheus that understands the native Prometheus data type and allows you to do that then without schema creation. Prometheus will be a cache of the data and will be the long-term storage. So when you miss in Prometheus, Prometheus will talk to us. And similarly, Grafana or other parties could query us directly. And so we could use our full SQL support and even advanced analytical functions. So now you could talk through Prometheus via PromQL or talk directly to Timescale via SQL and the UDFs that we expose. Okay. And so before I get there, let me talk about two things. One is how do we scale up performance, and also how do we make it easy for Prometheus? That is, how do we avoid the schema problem? To give a high level, this is somewhat pure Timescale. And if you think about time series data, you have all these devices, all these servers dumping data at you. And typically, they're writing about recent things that happen. Right? So all the writes are basically really are inserts to latest time intervals. And so the one thing that we do is we basically do this automated space-time partitioning. And so you can basically define an interval either manually, or we also have an experimental branch that will have the database automatically adjust this intervals based on perceived performance of the database. And also some 0 to many additional dimensions. And so under the covers, you are just interacting with what we call, and each of these actual pieces in this shown here two-dimensionally, we call a chunk, are actually stored in Postgres as a table. But you, as the user, are just interacting with what we call as a hypertable, which to you just looks like one big Postgres table. And what that means is anything that you want to do to a traditional database table, you do the hypertable. You could write triggers, you could define UDFs, you could write constraints, dynamically create any type of index, have any type of data type, use upserts, do table management. This all goes to the hypertable. You don't know of the fact that underneath the covers, we're doing this heavy and automated partitioning. And the database, as you insert new data, as it basically defines new intervals, the database is dynamically creating these new chunks, these new tables, is putting all the right indexes and constraints and everything in the chunks so everything happens kind of automatically. And the benefits of these are twofold, or severalfold. One is that we're basically sizing these recent chunks. So as time series workloads come in, and all the recent writes are basically to latest intervals, these intervals, these chunks naturally stay in memory, which means that you avoid that basically performance cliff that you saw with Postgres as you're going to one table. And particularly, it's that the index is built on table. Even though, again, the writes are to the recent data, if you want to maintain indexes on that table, you need to insert those indexes into the right index sorted order. And that's the thing that could constantly swap back and forth the disk. All of our indexes are local to the chunk, so they all stay naturally in memory for the latest data. The second thing that we could do is we basically allow you then to, today in the open source version, scale up even on a single node by dynamically and elastically adding more disks. So we could take this one hypertable and spread it across many disks, either via RAID or Postgres' native support for table spaces, which means you could have a running database in like AWS. You could elastically add a new EBS volume, run a command in the database, and now your single table is going to use that new disk, that new EBS volume, in addition to all the existing ones. And this leads to basically faster inserts and also basically parallelized queries. We've had people run on something like 25 disks off of a single instance. And we are under development. We hope to launch by the end of the year, is basically scaling this out, then taking the same design and scaling across many disks. The interesting thing is, when you talk to a lot of people, they're like, yeah, but going from single to distributed is very hard. This is not undercutting some of the engineering challenges, but it's also the observation that even on a single node, we basically are doing a lot of the things with distributed queries, predicate pushdown, various things you think of in distributed settings that we're actually already doing on our single node, given our kind of heavily sharded or micro-sharded design we already use. And one of the reasons performance gets better is in time series data, you often are doing things with predicates related to these partitions. So for example, you say, if you're doing monitoring, if you're doing a dashboard, give me data about the last 7 days, about a particular device. And so this is going to use those type of the constraints that we know about those shards to figure out, I only want to run this query on these three chunks. Or I could slice across many devices, but say, tell me about all my data over the last 24 hours. Now I could choose, the query planner is going to figure out which of these chunks to exclude and going to only query those ones that you need to. And I want to observe that this is actually quite fast in timescale, but actually not fast in native Postgres. Ignoring all the partitioning stuff, because effectively we have a concept of time that now here is a function, and from the database perspective, it just looks like an abstract function that doesn't know how to reason about. Because we built in special support for time, we could really make these type of analysis at the query planner level. And the last thing I want to point out is that what this type of does is allow you to do things like efficient retention policies. So this allows you in the database not to actually want to delete individual rows. But you could say things like delete all chunks that have all their data over a week old. And then what you're really going to be doing is just deleting files from disk, as opposed to in a single table where you delete individual rows, which would basically you need to then defrag or vacuum or garbage collect your tables, which is quite expensive. So this makes data retention policies much more efficient. And so all this stuff actually, the second question is how easy is to use. And to point out, this is basically that middle line in red is the only thing you need to get started. If you look at the top, I basically created a schema like you would in any relational database or any schematized database. I run this one command, create hypertable, which is basically turning this into a hypertable, telling us how we want to do intervals and partitioning, and then I insert it and select from it like anything else is new. In fact, if you want to change things, you could dynamically change these intervals, you could change this dimensionality of your partitions, and that again is very easy to operate. Now, some of you who might be Postgres users might say, yeah, but doesn't PG10, Postgres 10, which released last year, have like this special support for like declarative partitioning and native partitioning? And the answer is kind of. So if you remember this graph before where I basically say, here's the database and here's the table, create a hypertable, the equivalent to do this in PG10 would look like this. So you need to manually basically create all of your partitions, both on here would be devices or times. You need to manually create all these indexes connected to it. This obviously is a lot more manual work. And as I'll touch on in a minute, like maybe this is okay if you only create monthly partitions. But if you want to reach the fine grainness you want to keep everything in memory, if you have high volumes of data, you actually might be creating partitions every few minutes, which is what we have in some of our deployments. So this is not going to work. And I'll come back to this in a minute, but just to give you an example of what all of this design gives you, if you remember my graph before in blue, this is a similar graph now running in timescale. And you could say, and now if you want to go from batch size of inserting one row at a time, you want to basically feed this off of something like Kafka, and you're inserting 10,000 rows at a time. You go from timescale being able to support on a single moderate Postgres instance running on Azure over 1 million metrics per second to Postgres, which is 1/20th the capacity, the throughput capacity. So kind of this architectural design designed for time series data gives you real throughput. And going back to Postgres 10, it's not only ease of use, it's also performance. They don't really design for large numbers of partitions. So this is the same graph of throughput, and the blue line is actually Postgres 10 as the number of partitions turns into the hundreds of thousands. And I alluded to this before. So we've had individual users who've taken a single hypertable, what looks like a table to the user, have stored 500 billion rows on this, doing 400,000 inserts per second. And if you do the math, this basically translates the database dynamically creating a table every few minutes. And again, that's not something you're going to be doing manually. And so it gives you kind of insert performance and then a whole lot of query performance, particularly around things where the database could reason about time-ordered group bys, which are, again, very common in monitoring. Select bucket by 5-minute interval, give me a metric, an average or standard deviation or histogram over that 5-minute interval, group by that interval, order by that interval descending. That's something that we handle very quickly, but you won't get natively actually out of Postgres. Okay, so hopefully I ran through and gave you some ideas about these top 3 things. So the latter question is what about the schema thing? Isn't that still annoying? I don't want to deal with schemas when I just do monitoring. And so I want to talk a little bit about how we actually now added this for Prometheus. And we released another extension from Postgres called PG Prometheus. You could use it with basic Postgres. You don't have to use timescale, but for all those other reasons, you really want to be using timescale. But effectively, what it does is it ingests what looks like native Prometheus data lines. So if you look at the later line, you create tables metrics, and this type is a Prometheus sample, or is a sample. And then the value is that string is basically the format of a Prometheus record, right? It has a bunch of labels, it has metrics, it has a timestamp, whatever. In fact, the interesting thing is you actually don't even need, once you have this, you don't even need Prometheus. You could just with curl, you could actually go to another endpoint, grab a bunch of metrics and ingest them directly into the database, even as simple as, these 1 line of code, right? Okay, but now we have this line. The nice thing is you could actually query the database for it. So you could just select star for metrics and you get back what looks like this string. But we have typing around this. So you could also do something like select and then give it a function, Prometheus time, Prometheus name, Prometheus value, and you could actually get schematized values of each of these. And internally what we do is, perhaps not surprisingly, we leverage support for JSON or binary JSON to store all the labels in JSON, and then we actually store the other things actually as their own columns. So native type, so indexes become faster and all these things. That's just selecting, but and I kind of alluded to this, and what we actually also added was the ability to not only have denormalize, because you don't really want to be storing all the labels with every data record. It often gets very wasteful of space. So we also have added the support to even normalize your data storage and really use the power of it being a relational database. So here you could just, again, call select create Prometheus table. And what that means is your metrics will now go into metrics table, one of these hyper tables. And we are instead now storing your labels and a reference between them into a regular relational table. And in fact, we create foreign key constraints between them. So you don't have to think about that. But it all ensures referential integrity. You could do delete cascades and all the things that you get from that you'd like from a relational table. And we actually also then create a view over both of these. So you don't have to realize that these are now, you don't have to perform the join. It will actually, the database will perform this for you. And it will properly index all this stuff. And so what that leads to is now you could use your Prometheus data and do very natural queries. So here is basically a give me all the data in the last 10 minutes, now minus interval, where the metric is CPU usage, and this little @ sign is kind of a Postgres specific thing for accessing JSON, but it's saying, and the label matches, it's basically an equal sign, has a service label of Nginx, right? So this is one kind of SQL statement, and this will allow you to do kind of slicing and dicing with the query planners and everything on your relational data. What this then means is you could then point Grafana against this. So as of a few months ago, actually, Grafana added a Postgres connector. So if you look at the above graph and you look at what I will show you is a zoom in, this is actually a query from Grafana to a timescale database that, for the most part, you could see it uses this label. So this is taking advantage of even the JSON support inside timescale and Postgres, is using some timescale specific function. So time bucket is something that Postgres doesn't support, which only allows you to really date trunk by minute, hour, whatever. We allow you to do could be 5 minutes. We allow you to do arbitrary bucketing, basically UDF and timescale. And now you can make this directly from your Grafana instance into timescale. But like I said, you could actually query in both ways. So instead, you could use a query builder. This is actually speaking PromQL. And so this is actually your same Grafana instance that is now querying Prometheus. If Prometheus locally has it, Prometheus will return it to you. If Prometheus doesn't have it, Prometheus will now speak to timescale, pull it, cache it at Prometheus, and return it to Grafana. So it really is, the flexibility is up to you, but the advantage of you have this ability to now ask very rich questions about your data And my understanding is the author who partially did this for Timescale, who released the SQL connector, is just about is in the process of building a query builder. So you could actually do the same type of query building, but now for Postgres and Timescale data. So together, this kind of gives you the ability of all these things working together, and hopefully solve some of the problems you had before by basically achieve both scale, and you could ask, why don't you use Postgres for metrics? And with Timescale and now with this integration, it gives you support for both doing it at scale and actually also basically not having to manage your schemas yourself. So with that, I'll skip over these, and anything we talked about, these are all the things I talked about today are released as open source on GitHub, and happy to have people also join our community on Slack. So take questions. So Timescale today supports Postgres physical replication. So you can, and we have people deploying us into production that has, the single primary node, and then actually multiple read-only replicas. All the writes go to the primary. They automatically get replicated via physical replication to the replicas. You could actually do read-only queries to the replicas, and of course, there's tools where you could actually have the replica now take over the primary when the primary fails. So that gives you both scaling out the query, the number of concurrent queries you could support, as well as actually HA support. We are working, like I said, we are working on our scale-out clustering. I think Citus's model is a little bit different. They are really focusing, in many cases, to this to multi-tenant like SaaS applications, where they first partition by the tenant and then allow you to do something else. They recommend, I think, you could use something like pgpartment to do some of this. But I think if you look at what there was a lot of engineering that went into this work transparently. The fact that basically all of your writes and all of your alter commands and all the thing that you send to the hypertable just propagate correctly down to all the subtables. Even your internal things where the way you do chunking or reindexing or fill factors, all these things kind of work directly out of the box. And if you look at most of the other techniques for partitioning, this is not the case. I think upserts are a really great example. So for people who don't know, an upsert is update if a row exists, or otherwise you could insert it. Or insert, and if it already exists, it converts to an update. This uses constraints. None of this stuff, this does not work in Postgres and PG10 or whatever. And the reason that turns out to be really important, particularly for time series data, is a couple different use cases. One is you're collecting data on IoT in the edge. You don't want the edge to have to think about exactly one semantics. You want the edge to be able to send you data and you insert it. And if the edge went offline and then come back online and resend you the same data, you don't want you to have duplicate records in your database. The second thing this really is good for is to roll-ups and aggregation. That you want to basically continuously roll up and basically take your raw data and move it to 10-minute roll-ups. And if you get late data, that is, the 10-minute marker has already passed, but some device or some ticker or whatever has been reported late back to an old entry that you've already rolled up. In many of the existing time series databases, you just never see that data because you run it, you roll it up at the 10-minute interval and you never go back. But because we have this ability to do upserts, that late insert basically could trigger a new roll-up that will safely recompute it. So there's a lot of things that we do to make this stuff work the way you'd want it that a lot of the other partitioning techniques don't. What we find, so in a lot of, in the traditional OLAP thing, they have all these designs with star schemas and all these relationships. We have found that sometimes those type of things exist, but usually your data models for some of these time series workloads we're looking at are much simpler, in that you have often one big time series table and additional relational tables which hang out of it, but not this like crazy star model that the OLAP world got into. The second thing about table design is this is kind of related to also your schema design. So a pretty common thing in this is one way to do is store a very simple row where it's value name type, which is what you saw in some of the ways we did Prometheus, that we wouldn't need to dynamically create each table for different data types. They would actually be all stored in different rows, and one of the columns is actually the name of the metric. That is one way, for example, to do schema design. So I would agree with you that kind of there is some thought having to do with table design, but I would say that often the type of scale applications we've seen people come across, there's perhaps less of this than in some of the kind of analytical queries that traditionally came from the data warehousing world. We don't currently allow you to specify that, but my comment is that that naturally happens given the workload. The question is this: when do you have memory pressure? You have memory pressure when people are asking for more data than you fit in memory. So the question is, what should a database do to say, if you say, I want you to preserve the last 2 hours of stuff in disk, and then another query comes on and touches a lot more stuff and you don't have enough memory. So do you crash with an out-of-memory error, or what? In some sense, if you are over-constraining what, your constraints, that is, you are making these hard constraints, you don't have enough resources, something bad has to happen. Either you violate those constraints, or you basically crash. Generally, I don't think we want to crash our database if we could swap and degrade performance a little bit. This is something I think we'll think about, of what it would mean to prioritize like pinning certain tables. Right now, what we're doing by that is really taking advantage of the way the operating system is fetching pages and whatever, given workload patterns. But maybe there's some hints that we could use from users to prioritize something. The one thing that we do is, again, with this, because we support multiple table spaces, you could actually bring disks of different types. So you could, for example, be storing fresher data on, like, let's say, provisioned SSDs and older data on hard drives. And that's a different way you could actually manage the same problem.
All right. Well, thank you.
Thank you.